Hi guys, so we had just talked about how the different components of our angular momentum do not commute with each other, and so they are considered incompatible observables, and we can look at uncertainty principles related to that. And we were just about to start out with talking about how the square of the angular momentum does commute with our component Lx. So let's start there. So our goal is to talk about the square of our angular momentum and how it commutes with Lx, and to show that this commutator relationship is zero. So if we look at what our definition was of the square of the angular momentum, it had three components. So we can split this off into how does our one component Lx commute with these three different components. So I'll write that out, that we have an Lx squared, an Ly squared, and an Lz squared, and we're looking at how each of those commute with Lx. Now, of course, Lx is going to commute with itself, so that portion of this is going to go to zero. But we're going to have to look a little more closely at the next two things. So when we look at those, and this is just a relationship, you might need to do a little brushing up on this kind of math. When we look at those, we can pull this Ly squared, which just means we're applying it twice, outside, and we pull it outside in both directions to look at how these operators commute. And then we do the same thing with our Lz. We pull it outside in both directions. So I have one more thought to put down here, because I didn't manage to fit it all on one line. All right, so we have those four components to consider. Well, this works out because we had just done this kind of commutator relationship. It is what I boxed on the previous page, right? So let's find where that is. It is what I have boxed right here. So we can go to this page and say that we want to know about those commutator relationships. So in red, let's switch that. So when we go to this relationship, we've got L squared Lx. We've got our operator Ly. And then the commutator relationship from Ly to Lx. Well, remember I said the order matters. So switching the order just puts a negative sign in front of that we had already figured out. So negative I h bar Lz, and then Ly, and then Lz. This goes from Lz to Lx, so that's going to give us I h bar Ly, and this last one is going to be I h bar Ly Lz. So when we look at that, the IH bar that you've got here, the negative IH bar and the IH bar here, it doesn't matter where they go with these operators. They can go in front here. And so we've got a negative IH bar, Ly, Lz. We've got the positive one here as our last component. We can see that these two things cancel out. Similarly, with our middle items, we've got Lz and then Ly is the order of our operators. So remember, order matters. And we can see that these two things cancel out. So we do get to the result that we were trying to get to, that the square of our angular momentum does commute with our x component. And in fact, you can also show with similar arguments that the square of our angular momentum commutes with Ly, and also commutes with LZ. So if that is the case, when you do this math, you are saying that the square of your angular momentum commutes with the vector of the angular momentum, with each component of the vector. So if the square of the angular momentum is compatible with each component of that vector, we should be able to find simultaneous eigenstates of the square of our angular momentum and each of these components. So we should find simultaneous eigenstates, which is to say we should find simultaneous allowable angular momentum for the square of the angular momentum and one of the components. So you could say LZ or LY or LX. To write that in an eigenvalue equation, you have the square of your angular momentum is going to give you an eigenvalue. So the square of your angular momentum as an operator acting on a function should give you an eigenvalue multiplied by that function, but also that if you took the operator for one of those components acting on that eigenfunction, you should find a simultaneous eigenvalue. And those functions are your eigenstates. So we'll pick up there with the next one. Try to keep these in bite-sized pieces.